We've already seen that if we were to start with the differential equation, the derivative of y with respect to x is equal to y, and we had the initial condition that y of 0 is equal to 1, that the particular solution to this, given this initial conditions, is y of x is equal to e to the x, or I guess we could just say y is equal to e to the x if we didn't want to write it with the function notation. And that's all fair and well, and this works out well. This is a separable differential equation, and we can integrate things quite easily. But as you will see as you go further in the world of differential equations, most differential equations are not so easy to solve. In fact, many of them are impossible to solve using analytic methods. And so given that, what do? You've nicely described some phenomena, modeled some phenomena using the differential equations, but if you can't solve it analytically, do you just give up? And the answer to that question is no. You do not just give up, because we now have computers, and computers are really good at numerical methods for approximating and giving us a sense of what the solution to a differential equation might look like. And so how do we do that? Well, in this video, we can explore one of the most straightforward numerical methods for approximating a particular solution. So what we do is, so let me draw a little table here. So a little table here. And so, actually, let me give myself some, I'm going to do it over here on the left-hand side. So, a little table. So, x, and then y, with x, y, and then dy, dx. And you could set up a table like this to create a slope field. You could just pick you could sample x's and y's in the xy plane, and then figure out for a first order differential equation like this, what is the slope going to be at that point, and you could construct a slope field. And we're going to do something kind of related, but instead of trying to construct a slope field, we're going to start with this initial condition. We know that y of 0 is equal to 1. We know that the particular solution of this differential equation contains this point. So we're going to start with that point. So we're going to start with x is equal to 0, and let me do this in a different color. We're going to start with x is equal to 0, y is equal to 1, which is that point right over there. And we're going to say, well, okay, what is the derivative at that point? Well, we know the derivative at any point or for any solution to this differential equation, the derivative is going to be equal to the y value. So in this case, the derivative is going to be equal to y. It's going to be equal to 1. And in general, if the derivative, just like what we saw in the case of slope fields, as long as the derivative is expressed as a function of x's and y of x's, then you can figure out what the slope of the tangent line will be at that point. And so you say, okay, there's a slope of 1 at that point. So I can depict it like that. And instead of just keep doing that at a bunch of points, we'll say, okay, well, we know that the slope is changing, or it's probably changing for most cases, but let's just assume it's fixed until our next x, and then use that assumption to estimate what the next y would be. So what am I talking about here? So when I talk about the next x, we're talking about, well, let's say for the sake of simplicity, we're going to have a delta x of 1. A change in x of 1. So we're going to step from x equals 0 now. We're going to now step from that to x is equal to 1. So we're now going to go to, actually, let me not use that. I used that yellow color already for the actual graph, or for the actual e to the x. So now let's say x is equal to 1. So our delta x is 1. So we've just added 1 here. And what we can do in our little approximation scheme here is, well, let's just assume that slope was constant over that interval. So where does that get us to? Well, if y was at 1, and if I have a slope of 1, for one increase in x, I'm going to increase by y by 1. So then y is going to increase by 1 and is going to get to 2. And we see that point right over there. And you already might see where this is going. Now, if this were actually a point on the curve, on the solution, and if it was satisfying this, what would then the derivative be? Well, the derivative is equal to y. The slope of the tangent line is going to be equal to y. So in this case, the slope of the tangent line is now going to be equal to 2. And we could depict that. Let me depict that in magenta here. So it is going to be 2. So it's going to look, the slope of the tangent line there is going to be 2. And so what does that tell us? Well, if we step by our delta x one more, so now our x is equal to 2, what should the corresponding y be? Well, let's see. Now, for every one that we increase in the x direction, we should increase 2 in the y direction because the slope is 2. So the very next one should be 4. Y is equal to 4. So we could imagine we have now kind of had a constant slope, and we get to that point right over there. And now we can do the same thing. Well, if we assume dy dx based on the differential equation has to be equal to y, we can say, okay, the slope of the tangent line there is going to be the same thing as y. It's going to be 4. And so if we step our x up by 1, if we increment our x by 1 again, once again, we just decided to increment by 1. We could have incremented by 10. We could have incremented by 0.01. And you could guess which one's going to give you a more accurate result. But if we step up by 1 now, and our slope is 4, well, we're going to increase by, if we increased x by 1, we're going to increase y by 4. So we are going to get to 8. And so we are at the point 3, 8, which is right over here. And so for this next stretch, the next stretch is going to look like that. And as you can see, just by doing this, we have been able to approximate what the particular solution looks like. And you might say, hey, Sal, well, that's not so good of an approximation. And my reply to you is, well, yeah, I mean, depends on what your goals are. But I did this by hand. I didn't even do this using a computer. And because I wanted to do it by hand, I took fairly large delta x steps. If I wanted a better approximation, I could have lowered the delta x. And let's do that. So let's take another scenario. So let's do another scenario where instead of delta x equal 1, let's say delta x equals 1/2. So once again, x, y, and the derivative of y with respect to x. So now let's say I want to take, so we know this first point, we're given this initial condition. When x is 0, y is 1, and so the slope of the tangent line is going to be 1. But then if we're incrementing by 1/2, so then when x is, I'll just write it as 0.5, 0.5, what is our new y going to be? Well, we're going to assume that our slope from this to this is this slope right over here. So our slope is 1. So if we increase x by 0.5, we're going to increase y by 0.5, and we're going to get to 1.5. So when we get 0.5, 1.5, we get to that point right over there. Actually, you're having trouble seeing that. This stuff right over here is this point right over here. And now our new slope is going to be 1.5, which is going to look like, actually not quite that steep. I don't want to overstate how good of an approximation is, and it's starting to get a little bit messy, but it's going to look something like that. And what you would see if you kept doing this process, so if your slope is now 1.5, when you increment x by another 0.5, well, you get to 1. So now if you increment by 0.5 and your slope is 1.5, your y is going to increment by half of that, by 0.75, and so you're going to get to 2.25. So now you get to 2.25, which is this point right over here. And once again, this is a better approximation. Remember, in the original one, y of 1, should be equal to e. Y of 1 in the actual solution should be equal to e, 2.7, on and on and on and on and on. Now in this one, y of 1 got us to 2. In this one, y of 1 got us to 2.25. Once again, closer to the actual reality, closer to e. Instead of stepping by 0.5, if we stepped by 0.1, we would get even closer. If we stepped by 0.0001, we would get even closer and closer and closer. So there's a bunch of interesting things here. This is actually how most differential equations or techniques that are derived from this or that are based on numerical methods similar to this are how most differential equations get solved. And even if it's not the exact same solution or the same method, that the idea that most differential equations are actually solved, or I guess you could say simulated, with a numerical method, because most of them actually cannot be solved in analytical form. Now you might be saying, hey, well, what method is this one right over here called? Well, this right over here is called Euler's method, after the famous Leonhard Euler. Euler's method. And not only actually is this one a good way of approximating what the solution to this or any differential equation is, but actually for this differential equation in particular, you can actually even use this to find E with more and more and more precision. Anyway, hopefully you found that exciting.